Welcome, I'm Maciej, and I'm going to present our recent work on high-performance parallel graph coloring. Graph coloring is one of the fundamental problems in graph theory, in which we assign numbers that we call colors to each vertex in such a way that no two neighboring vertices share the same color. The goal of the associated algorithms is usually to minimize the number of used colors. In terms of applications, graph coloring has many of them. For example, in constructing schedules or timetables, when assigning frequencies to radio towers, when allocating registers, coloring maps, and even for solving Sudoku. Let's take a look at graph coloring in the context of today's graph computations. On one hand, graph datasets are huge, as shown by recent papers. On the other hand, we know that optimal graph coloring is NP-complete. This means that this is infeasible to try to color such huge graphs using the optimal number of colors. Then we have massive parallelism, which led to the interest into developing parallel graph coloring heuristics. Many of these heuristics have a shared common structure in which we iterate over all the vertices, ordered in some order, from V1 to Vn, grab each of these vertices Vi, and then find the smallest color C, which is still not assigned to the neighbors of this Vi, coming before in this order that we use. After we find this color, we assign it to Vi. So this immediately gives us the theoretical bound on the maximum number of colors to be used, namely maximum degree plus 1, because this is really the thing we will have to do in the worst case, because in the worst case, this vertex Vi will have delta neighbors previously in this order. So we need delta plus 1 colors in the worst case. And this order that we are picking the vertices in impacts the coloring quality. Now this looks very simple, but also sounds quite sequential. And the parallelism is enabled in this scheme by grabbing in parallel groups of vertices for coloring which are not adjacent to each other, so they are not forming an independent set. We'll refer to this family of schemes as the scheduled coloring heuristics, because really this vertex order that we are using is the central piece, and it determines intuitively, it schedules the moment where each of these vertices is picked for being colored. Two main goals of such heuristics are, on one hand, to maximize quality, namely minimize number of used colors, and to maximize performance. And these two goals usually are usually considered for both the empirical setting and for the theoretical properties, where we want to minimize work and depth. Where work is the total number of operations that we use in the algorithm, and depth is the longest chain of sequential dependencies. And we also want to minimize the theoretical bound on the number of used colors. Many such heuristics were proposed, and they come with different trade-offs between work, depth, and quality. They are all based on some ordering. So you may use different orderings. Name here in this column illustrates the intuition behind each order. For example, largest degree first prioritizes vertices with larger degrees. And then using these orderings, we can construct the associated coloring heuristic that comes with some depth, work, and quality. For now, we'll not take a look at these details. This we'll do later in the talk. What is important to realize is that this ordering is some kind of algorithm itself. So it comes with some bounds for work and for depth. And then the associated coloring heuristic based on this order is usually having different depth and work bounds. Now, another important observation in this table is that almost all of these schemes for coloring have only trivial quality bounds, these delta plus 1 bounds that are like immediately falling out from the overall general formulation of this heuristic. The only scheme that has good quality bounds based on the parameter called graph degeneracy don't really have general bounds for depth, only some worst case analysis. Let's try to grab this scheme and see if we can use it as a basis for something more powerful. The scheme is based on the ordering called smallest degree last, and really the intuition, really the core of this ordering is to iterate over all the vertices in the so-called degeneracy order. To introduce this, we need some definitions. First, we say that the graph G is S-degenerate if in each of its subgraphs or induced subgraphs, there is always some vertex with a degree of at most S. Intuitively, this means that if we grab any induced subgraph in some graph, we must be able to always find at least one vertex with degree at most S for any such selection. Then this concept is used for a different definition, the so-called degeneracy D of a graph G. So this is really the smallest s such that G is still S-degenerate. Intuitively, this degeneracy notion captures the graph sparsity at any level, namely that for any selection of the subgraph, we always find some sparsely connected vertex in this subgraph. Of course, the lower the degeneracy is, the sparser the graph is. Now, we remember that this coloring heuristic based on this degeneracy ordering gives a provable D+1 coloring quality. This sounds very promising because modern graphs are sparse, so we can hope that this D+1 should be low in practice. Now, the final concept that we need is the degeneracy ordering itself. So it's really an ordering in which every vertex V has at most D neighbors, where D is graph degeneracy, that are ahead of V in this order. Let's take a look at another example. We grab some graph and let's just say this graph is free degenerate. Then we order the vertices by just putting them on some line. And so this is a degeneracy ordering of this free degenerate graph because we can now double check and verify that for each of the vertices, it will have at most 3 neighbors ahead in this order. How do we derive this ordering? Well, it's very simple. We sequentially iterate over all the vertices. We grab the one with the smallest degree and remove it from the set of all the vertices and proceed like this. It means that in the main loop of this algorithm, we iterate over in this loop until this V is empty, and then in each of these iterations, we grab the vertex V min, which is the smallest degree vertex, and we remove this vertex from the set of vertices and then assign the rank. Now deriving this order takes O and depth, so it's really inherently sequential, and it also is the bottleneck for the performance depth of the coloring heuristic, which is based on this order. So here our key idea is to move away from the strict degeneracy ordering and introduce some form of relaxation that is going to have some accuracy loss, which is going to be provable and thus also amenable to theoretical analysis. So we call this ADG, Approximate Degeneracy Order. And here we again iterate over all the vertices, V. But instead of picking a single vertex with the smallest degree, we pick a bunch of vertices that form a set R min of the vertices such that their degrees are smaller or equal the average degree in this set V times a certain factor, which is 1 plus epsilon, where epsilon is a parameter I'm going to explain in a couple of seconds. Then we take this set of vertices R min and we remove this set from the set V. And then in the final part of the given iteration, we assign in parallel the rank, namely the current iteration count, to all these vertices that we are just removing. Now this epsilon is a user-specified parameter that is a way to control the trade-off between the performance and the quality. So the larger epsilon is the more loose we are in terms of what vertices we are considering for the set R min, and the set R min will become larger for the larger epsilon, meaning that we are going to have fewer iterations, and thus this will translate to somehow more performance, but at the same time this also may weaken the accuracy. If epsilon becomes smaller, then we are getting closer to the strict degeneracy order, but at the same time we increase the number of iterations, and this means that we may lose some performance. If we take a look at this algorithm in more detail, realize that on one hand, constructing the set R min will take O of log and depth. The key part here is to construct this average degree in the set V. Subtracting this R min from V will take O of 1 of depth, simply because we can store both as bitmaps. And then assigning the ranks also is O of 1. It means that a single iteration takes O of log and depth, which is very nice. Then we can also prove that by using this value of this condition for constructing R min based on grabbing this set of vertices with these degrees guided by the 1 plus epsilon factor and the average degree, this R min will form a constant fraction of all the vertices in V. And this fact can be used to prove the fact that there are O of log n iterations in total, giving the final log square and depth. Finally, a similar analysis gives us the bound on the work, which is going to be linear in the size of the graph. So to sum up, we move away from the strict degeneracy order, which comes with linear work, but also linear depth, to a scheme which is called ADG, which also comes with linear work, but the depth is polylogarithmic. But it comes with a certain amount of approximation, which is going to be which is equal to 2 times 1 plus epsilon. Now this is still just the ordering itself. And there is a question, how does it impact the actual graph coloring heuristic? For this, we need to understand again we need to understand in more detail how this coloring works in tandem with a given vertex order. So let's again take a look at an example. Let's start with again the strict degeneracy ordering. We remember this example. We have here the degeneracy ordering of a free degenerate graph. Then to color the vertices according to this order, once we have this order, we simply iterate over these vertices from the right to the left. And at each step, we grab the next vertex and we consider its neighbors on the right. And we remember that in this ordering, there must be at most d neighbors on the right. And this means that we will immediately see that the maximum number of colors that we may use is d plus 1. Now in our ADG scheme, this is very similar, but this time we have this relaxation, namely we have this approximate degeneracy ordering with the approximation factor of 2 times 1 plus epsilon, and that many more neighbors we may have in this order on the right. So, but again, we proceed in the same way. We grab each vertex, and then we assign the smallest color node being assigned to the neighbors on the right. And this means that we will use at most 2 times 1 plus epsilon times d plus 1 colors in our ADG scheme. So if we now take a look at this table, we add our ADG scheme at the bottom, and the quality bound that we are going to have is only a little bit more than twice as worse in the worst case as the quality bound for the scheme based on the smallest degree last order that uses strict degeneracy ordering. Now let's continue with getting the bounds for depth and for work. We did this analysis for ADG, but again, we are interested in really the bounds for the coloring itself. To do this, to get these bounds for the coloring heuristic based on ADG, we consider a directed acyclic graph, a DAG, which we impose over the input graph G. So we are just taking our input graph and we assign directions to each of these edges in such a way that that edge goes from vertex 1 to vertex 2, if and only if this vertex 1 is higher in the order than vertex 2. So this formulation is very general. This DAG can be constructed for any ordering of vertices. And in our case, we of course consider ADG. But in general, this is a very general formulation. And it was proved in the past that such a parallel heuristics that uses this DAG formulation combined with some order will always run in the depth of O of size p times log delta plus log n, where n is the graph size, delta is the maximum degree in the graph, and now p is the longest of the paths in this DAG. Right, so this means that for our analysis, we already assume that delta is known, and we of course know n. So now the only question that remains for this analysis for depth is to find the longest path in the graph that is in the DAG, which is constructed using the ADG ordering, and then plug in this value of the size of this path into this depth bound that we can get from existing work. This is really the main question here. What is the size of this longest path in this DAG imposed over the input graph based on the input graph that is based on the input graph and is using the ADG ordering? So the intuition, the sketch of the intuition of our proof is that on one hand, we know that vertices with the same ADG rank form some subgraphs, right? So we remember we are in each iteration, we are grabbing some batch of vertices, and these vertices are going to share the same rank in this ADG order. So this ADG is really a partial order. So this means that they will also form some subgraphs. Now, on the other hand, as we are analyzing the longest path in the whole graph, this is a DAG that we are considering. We can analyze this length by analyzing the lengths of the paths that are parts of this longest path P and belong to different subgraphs. And then we can try to get these lengths of these parts for each of these subgraphs and sum them to get the final length. That's exactly what we are doing in the paper. And we also use the properties of ADG to get the actual bounds. And by the properties of ADG, each vertex has only a bounded degree in each subgraph. So this really means intuitively that there is only as far as you can go in each of these subgraphs, and this far is really a constant. And using these facts with some randomization analysis gives us our bounds. These bounds are bounds in expectation. And if we compare now these bounds of the coloring based on the ADG to some most recent bounds, we'll see that we are not really that much different. So we do have this log square n factor, but on the other hand, for example, the second scheme in this table, this is also a recent one based on this on some approximation of different type of the strict degeneracy ordering, the smallest log degree last. This is coming with a product of log n times log delta, where delta is this maximum degree in the graph, so it is often not much smaller than n. So really the bound is not that much different, and we also see this in the evaluation that the results are also not really much worse in terms of runtimes. But again, we do have this this bound for the quality, which is much better than the bounds delta plus 1 present in most of these other recent schemes. That everything? Well, not really. So I was all the time saying about this scheduling-based parallel coloring heuristics, but there's also a second family, which is so-called heuristics based on so-called speculative coloring. I'm just going to sketch some intuition here. So in these schemes, so these are different schemes, and we also introduce a variant based on ADG, which also comes with some improvements. In this, in our scheme, what we are doing, we are now recording this ADG-induced partitioning. So before we only use this structure for proving our bounds. And now in our algorithm that we are doing here, we actually record this belonging of each of these vertices to this partitioning based on ADG-induced order. And now we color each of these partitions independently. So that's really the part where we do speculation. So this means that we are assigning colors to each of these partitions independently. There may be some conflicts. So there may be some connected vertices in different partitions that will have the same color. These conflicts are fixed by repeating the coloring as many times as needed. And our paper proved that using some randomization techniques, that with a certain selection of the parameters for this coloring scheme, this is going also to happen probably fast. So then we also can get some interesting bounds. Namely, in our main ADG speculative scheme, we have a depth bound that is derived with that holds with high probability, which is equal to log degeneracy times log square of n. So this is again a very interesting bound, because this log square n is not really much higher than these bounds in these other schemes, and log of degeneracy is going to be very low in most of the modern graphs, which are also quite sparse. Another interesting observation here is that this depth bound is really the only such strong bound for among all the schemes that are based on this speculation. Evaluation, we consider graphs of different origins for a wide evaluation, and a couple of different machines to make our evaluation as widespread as possible. Comparison baselines, we consider 16 algorithms that are based on both different orders and on different variants of different classes of algorithms, so scheduling versus speculative, and we use 4 existing libraries and implementations. Let's start with runtime and quality analysis. Here we pick some small example graphs, so a graph which has 5 million edges. Such graphs are used in various online settings. So the plot on the left is dedicated to the runtime analysis. The plot on the right is dedicated to the coloring quality. I apologize, I only labeled the y-axis button. So the y-axis on the left and the plot on the left is really just the simple speed up of the runtimes, and the y label on the right is the ratio of the coloring qualities after being normalized to the quality of the randomized scheme, and the numbers over the bars correspond to simply the counts of colors used in each case. And then on the x-axis, we are simply plotting different orderings that are used as the basis for a given graph coloring algorithm. On the left side of each of these plots, on the left side of these bars, we consider the speculative colorings, and on the right side, we consider scheduling-based colorings. The same for plot on the left and on the right. And also for the runtime plot, we also differentiate in these bars between the time for the reordering and the time for the actual coloring. And what we can see is that our ADG scheme is comparable on slightly worse in terms of runtimes in the speculative class, and somehow worse in runtimes in the scheduling class, up to 1.5 from the fastest schemes, such as largest log degree first. But we can also see that it's usually very competitive or better in both classes when it comes to coloring quality. So it's usually the best in the speculative class, and in the scheduling class, it's usually one of the best, being comparable or only slightly marginally beaten by other schemes, but this is only a single or two schemes that are really using the strict degeneracy ordering. So we can see that these schemes have very, very high pre-processing times, and this time really indicates this overhead for doing the exact degeneracy ordering. And this pre-processing time is then again like it really gives this very good coloring quality. So for example, on the plot on the right, we have 56 colors used, and the other scheme based on the exact order of degeneracy is using 55 colors used. But then we provide much less time for the pre-processing, again by providing this relaxation, and you can also tune this relaxation yourself depending on where do you want to go, whether for performance or for the quality. You can change this epsilon to make it behave more like you want. For larger graphs, we also consider larger graphs. The one here is having 230 million edges. The setting of these plots is the same. So again, on the left, we plot the simple speed up of the runtime, and on the right, we plot the normalized quality, normalized to the scheme based on the random graph coloring. And the outcomes are similar. So we are comparable or slightly worse than some schemes in the speculative class, and comparable or somehow worse in the scheduling class. In this particular graph, all the schemes have the same numbers of colors used, but in many other graphs, we are again comparable to the schemes based on the strict degeneracy ordering while being much faster in runtimes. We also analyzed scaling. Here we show the weak scaling plot where we use Kronecker graphs. On the x-axis, we different data points, increasing data points correspond to cases where we increase the number of edges per vertex, increasing the size of the graph, and proportionally increase the number of threads used. On the y-axis, we again show the speedups for total computation time for a given data set. The rounded rectangle indicates the schemes based on color scheduling, and the circle indicates schemes based on the speculation. In each of these two categories of schemes, we indicate our scheme with the bolded arrow, and we can see that we scale either similarly or slightly better than other schemes, especially visible in the speculative coloring class. We have much more data in the paper, and this data follows similar performance and quality patterns. To sum up, in our work, we developed novel parallel graph coloring schemes that enhance two established classes of graph coloring heuristics based on color scheduling and based on speculative coloring. The nice thing is that they almost always offer superior coloring quality than almost all other schemes. The runtimes are somewhat comparable or marginally lower than or higher than others in the speculative class, and somewhat worse in some cases than the schemes in the scheduling class, but again, always providing much higher improvements in terms of coloring qualities. And really the most important part that we think is the strongest point of our schemes is that they are the only schemes that come with non-trivial theoretical bounds on work and depth and quality at the same time. Thank you for your attention. I will now take your questions.